Should I just start? Or?
Yeah, sorry, yes.
Okay. Hi, I'm Radcliffe from the Global Open Finance Centre of Excellence, which is a non-profit being incubated in Edinburgh University at the moment, but we will be spinning out. GovCo is fundamentally based on the belief that there's real power in financial data that's not being properly tapped at the moment. GovCo is looking to find safe ways of better informing government, better informing decision makers, and allowing better access to financial data without compromising privacy or harming anyone in the process of doing that. We work with fintechs, we work with banks and other financial institutions to try and produce economic insights and to make data safely available for researchers in the context of an area called the Financial Data Safe Haven at Edinburgh University, which is a very locked down, very highly governed area for doing analysis. We apply very strong statistical disclosure controls. We only share data with a clear legal basis and follow the sort of 5 safes methodology, which is safe people, safe processes, and so forth. So we're trying to do it in the safest way possible. And things that we're doing include, analysing the impact of COVID-19 on both people in the UK and businesses in the UK. We're looking to do things like tackle algorithmic bias, to enable fintechs by providing them access to data that they don't necessarily have ready access to themselves, particularly in the startup stages, and tackling problems like social exclusion, sustainability, quality grading, stuff like that. And today I'm going to talk mostly about quite a bleeding edge approach to privacy preservation, which is the idea of using synthetic data. So I'm going to talk a bit about what synthetic data is and how we might be able to use it to advance these ideas. So to start off with, I guess, real data. Obviously, we all know what real data is, right? Real data, it describes real people and real events and real entities and so forth. And the advantage of real data is kind of obvious, right? It's real. But the fact it's real doesn't mean that it doesn't have any flaws. It can still be inaccurate, it can still be biased, it can be partial, it can still be misleading. And it has a surprising number of cons. The first obvious one is everyone is increasingly concerned about privacy, and no one wants, customers typically don't like the idea of people trawling over their real data, doing things. There are often access restrictions, there are ownership and licensing issues. And if there are biases in the real world, which there very clearly are, those biases necessarily translate through to the real data that you're working with and can cause all the problems we see about racist chatbots and unfair decisioning systems and so forth, the things that we call algorithmic bias. And the other thing that's true about real data is it's kind of limited to what's actually happened in the world. So it's more of a problem if you want either to imagine a different world and plan for that, or do what if and scenario planning and stuff like that. And often the data, the volume of data that you have access to with real data is limited as well. So there are all these things that are not as great about real data as you might think. Synthetic data, well, what's that? Well, it's exactly what it sounds like, right? It's fake data. It's stuff that you make up. It's stuff that, instead of being about real people, it's about synthetic people, dummy people we've made up, institutions that we've made up, and so forth. Or perhaps real entities, but still synthetic individuals. And so the idea, the thought experiment is, wouldn't it be great if we could do all the same analysis we're used to trying to do on a sort of dummy of the world, a synthetic double of the world, if you like, that has the same patterns in it, but doesn't have real people who could be harmed by the analysis that we do. Now, you can't achieve that in general. We'll probably never be able to achieve that in general, but you can produce synthetic data sets that are good enough for lots of analytical purposes that you're doing. What we're in the process of exploring how true that is today and what the potential for the future is. We're not primarily interested in developing the data science of developing synthetic data sets. We're planning to pick up both academic and commercial tools that are out there. We're primarily interested in using those in analysing the privacy impact and making sure that they're really safe in terms of not harming the people whose real data we're talking about. and checking the efficacy of it. In other words, can you actually produce valid insights from this? And that's what I'm going to talk about today. So, you know, a key point is that there's no such thing as just generically useful synthetic data. You'll hear from a lot of the vendors that their synthetic data generator will just produce a double of some real data that you can just use for all the same purposes as the real stuff. And that's not true. What's true is that there will be correlations between the two data sets, and it will be good for some purposes and not good for other purposes. But in particular circumstances, it can be powerful. In some circumstances, it can even be better than real data. Why is Kafka interested in this? Well, partly one of the things that Kafka has is an innovation environment where we're trying to make data available to fintechs. And we can't make the real data available that we have. So we often get de-identified data from banks, from other commercial organizations, but we can't share that directly for obvious reasons. But if we can create a synthetic double of that and make that available, that's a much more attractive thing for us to do. In our own data science work, we have this very locked down, secure, safe haven that is very safe, but it's quite painful to work in because it's very secure and locked down. And so we would like to do a lot of our work on synthetic data and potentially only apply it to the real data right at the end of the process, if we could. And there are also other tantalizing possibilities. There are ideas about being able to tackle algorithmic bias by producing data sets that don't reflect the same biases and historical injustices as are in the world. There are ideas about increasing model robustness by being able to do various different kinds of scenario planning. You know, what if we left the EU? Well, this was from a little while ago. You know, what if the Earth became uninhabitable for humans? How would that affect our business? It probably wouldn't be good. Financial crime. What if someone tried this thing that we haven't tried? Maybe we can test our systems against those kinds of things. So how do you produce synthetic data that might be useful? So this isn't a standard classification, but the way I think about it, I think there are broadly four ways of doing it. The simplest one, which has been used forever, is kind of pure random generation. So here, you know, we take the shape of the data we want, the sort of kinds of information we want, the fields and types and so forth, and we just generate random stuff from there. You might think, well, what use is that? That's actually remarkably useful for testing software that's supposed to be processing these systems. It can even be more useful than real data in many cases, because with random stuff, you get all sorts of outliers and edge cases that you won't necessarily see in any particular real historical stuff. But that's obviously, so it's good for performance testing, it's good for testing APIs and stuff like that, but it's clearly limited, it's no use at all for analysis. A more interesting approach is constrained data generation, where you at least try and get the right shape in each of the columns of data. So you try and get sensible distributions of, you know, whatever it is, transaction sizes, transaction types, of kinds of customers and so forth. But you don't worry about the really hard bit, which is the relationships between different columns, sort of cause and effect type stuff. But the two things that I'm mostly going to concentrate on, and where all the excitement is, are simulation, which is also sometimes called agent-based modeling, or the really modern stuff, which is model-based generation. So with simulation, the idea is that you essentially write custom programs that simulate the world. So you create, you know, if it's bank customers you're simulating, you create artificial people who have characteristics like jobs and characteristic incomes and family structures and locations and stuff like that. And then you have them interact with the world in various ways, and you generate data just as if they were real people. That can then be have good structure and integrity, have all the right properties, and you can control what they do. So that's been used for a long time, and is a very powerful way of generating complex data sets that have particular patterns that you want in, and that you can use for some of the sorts of things I was talking about, like scenario planning. What's difficult with simulation-based approaches is typically there's less variance, there's less variation, there's less weird stuff, there are less really strong correlations than you tend to get in real data. And so the latest idea, and the thing that I'm going to try and explain in slightly more detail, is model-based generation. The idea here is that you take some real data and you use machine learning to learn the characteristics of that data, to learn the relationships within a single table and between tables using different data domains. And then kind of reverse that process and use it as the basis for simulating data. I'll show you, that sounds a bit weird, but I'll show you how that works. So let's start off with a little sort of refresher on machine learning, in case not all of you are super familiar with it. How do you train a computer to recognize digits, for example? Well, very broadly, what you do in what's called supervised learning is you give it a whole load of examples of, in this case, images of zeros and ones and twos and so forth. And you give it what we often call labels, which are, you tell it what the right answer is. So what is this? This is a zero. What is this? This is another example of a zero and so forth. So, these are the left-hand sides, that you're trying to bring, and the right-hand side is what you're trying to teach the computer, essentially, the labels. And then you feed these digitized patterns in, and into some system that learns. You tell it what the right answer is, and it tries to learn from that. And I'll explain a bit more about how it learns in a minute. And then basically you mark it, so you then feed patterns in without the right answers, and the system makes its own prediction, and it says, well, I think that's a 0, and that's correct, so it scores a 1 for that, if you like. I think that's a 4, and it is, and that's a 4. Whereas this, if it predicts that as a 7, and we've decided that's really a 9, then we say that's wrong, and it gets negative. And essentially, conceptually, we just keep algorithmically twiddling the knobs until that learning system is pretty good prediction. I guess the only question is whether you need any more detail than that. It always sort of slightly reminds me of, I'm sure you've all seen the things about how do you draw an owl, right? First you draw 2 circles, then you draw the rest of the owl. Because I know everyone loves maths as much as I do, this is how machine learning works. I'll do it quite quickly. This is an example of a neural network, or what these days tends to be called a deep learning system. I actually did neural networks research. I actually did deep learning work when I was doing my PhD way back in the 90s, but I didn't realize it. I thought I was just doing neural networks at the time, but apparently I was doing deep learning. And the way these neural networks work is you have a load of nodes that are sometimes called neurons. And in the case of an image recognition thing, you just have one node for each of the pixels on the image that you're presenting in. And you just set those to a number. So the whites would be set to 1, the blacks would be set to 0, and the grays would be set to something in between. Right? And then they're connected together in this series of layers with weights between them. And you have outputs, which in one of the schemes correspond to the different labels that you're trying to predict. So if you're trying to learn this, what you would like is that you feed in a 0, and what ends up coming out is that the one node gets a 1 on it, and all the others get 0s on it. That's the ideal outcome. That's the pattern that you feed in. And these weights are adjustable parameters. And what the learning mechanism does is adjust the strength of these weights. And sorry, you don't really need to follow the maths, but actually it's much simpler than it looks. Basically, you just take the input, multiply it by this weight, sum all those together, pass it through a function that looks like this, a non-linear function called a sigmoid, that has that formula there. And then you compare the answer that you should get, the 1 if it's a 1 and the 0 if it's a 0, to what it actually is. Calculate an error, use calculus to feed that back through the network. And hey bingo, if you twiddle the knobs long enough, you actually know the system works. How do we know it works? Well, this is what's doing the voice recognition on your phone. This is what's doing the handwriting recognition on your phone. This stuff, 25 years ago when I was doing it, didn't really work. Well, it worked for some things, but it didn't really work all that well. It wasn't just because I didn't know what I was doing. It's because it's hard. But now we've got bigger data sets, more computing power, and it really does start to work. So, okay, that's machine learning. How do you use this for synthetic data generation? So one of the approaches is something called a generative adversarial network. And there are different ways of doing it, but one of the ways that starts off with is a thing called an autoencoder, which is a strange thing. It's exactly what I was just talking about, where you feed patterns in. But instead of trying to predict the label, what you're trying to have on the output nodes is to reproduce the pattern. So you feed a picture of a digitized 0 in, and what it's supposed to do is produce that same picture out. But what you have is a sort of squashed layer in the middle that forces it to try and form a compact representation of that in something called latent space. Why is it latent? Latent just means hidden. The idea is that the inputs are connected to the real world, the outputs are connected to the real world, but this stuff's all kind of hidden. And in these layered networks, essentially each network has a representation of the data. And so this is not a very interesting prediction task, you might think, to see whether you can, you can act like a bit of straight wire that just reproduces the input. But it actually is interesting because what you get here is this compact representation. And what it can do, for example, is you can feed in a damaged version of the picture. and it can essentially clean it up and recover it for you. It's one example. But you can also use this as a compression mechanism. So there are things called content addressable memories or associated memories, where the idea is you can feed in a partial pattern and recover the full pattern from it. So that's an associated network or an autoencoder. The interesting thing is, if you just look at the bottom of that, what you've got is a compact representation that produces stuff that's a lot like your input. And so it's a bit more complicated than this, but roughly speaking, the idea is almost whatever you set this latent space pattern to, you're likely to get something that's pretty realistic out from it. And so this is how you do the generation from that. And with generative adversarial networks, the adversarial component comes in that you have two networks, one of which is generating patterns like this, and the other of which you're feeding both synthetic data that you've generated and real data, and trying to get that network to predict whether it was a real pattern or a synthetic pattern. And essentially, the two things co-evolve, and every time the supervisor network correctly says this is fake or this is synthetic or this is real, it gets reinforcement, and every time it gets it wrong, it gets penalized. Whereas the generator network, every time it fools the supervisor network, it gets rewarded, and every time it fails to fool the supervisor network, it gets penalized and has to adjust its weights to make things better. And these things kind of co-evolve in a way that's shown here. But I won't go through the detail. So this is the general idea. Now there are lots of issues with this. This is bleeding edge stuff. It's not fully ready for the prime time. One of the issues is that just because the supervisor can't distinguish between synthetic data and real data, doesn't mean something else might. You might look at it and say, I can see that's fake straight away. Another thing you have to worry about is because these systems are trained on real data, you always have to worry about whether actually they're just kind of remembering the real data and might reproduce those things. And that's what a lot of the privacy work has to worry about, to make sure that either can't happen or isn't happening, or preferably both. Because what you obviously don't want is it just to kind of, you feed Nicholas Sturgeon in as part of your training set, and then it spits Nicholas Sturgeon back out as a real example. Because the whole idea is to learn the essence of people and the kind of variation there is, but not to remember the details of any particular question. And in machine learning generally, we talk about the idea of overfitting, which is where you do over-concentrate on the particularities of the data set. With machine learning, the idea is almost always to extract the essence, to extract patterns. It's the same thing. We're trying to extract the essence of human behavior, not the particularities. This person did this thing on this day. Let's spit that back out. And this stuff is certainly working. It's certainly had lots of successes already. A lot of it's being used in production. It's not bad for a lot of single table stuff at the moment, where you've just got a transaction stream, where you've just got a custom table. It's much harder when you want to have multiple tables with relationships between them, make all those coherent. But we are, if people are familiar with the Gartner hype cycle, we're probably still on the way up towards the peak of overinflated expectations, and there probably will be a drop afterwards. But there's no doubt at all this stuff is showing enough promise that it's definitely interesting. To say what Kafka is primarily interested in is figuring out how safe it is, because we can't use it at all if we're not extremely confident that it's safe and won't end up just leaking data. We're very interested in how useful it is as well in any task, but I guess the sine qua non is it has to be safe. And for us, the secondary thing then is how effective we can make it given that. Why are we well placed in this space? Well, A, we've got lots of academic credentials in terms of Veterinary University, but B, one of the things is we've got lots of useful data for training this stuff. And one of the ideas is we can give that to people and let them use it once we've determined that it's safe. If they're then not totally confident that they're not learning sort of artifacts that might be there in the synthetic data, one of the things we can do is potentially take whatever model or reporting system or whatever it is that they're using and run it against the real data in the safe location and check that the outputs that they're producing produce similar sorts of effects on the real data from on the synthetic data. And that's a way of building up assurance that this stuff's actually working. As I say, our main interest is in evaluating this stuff and making sure it's safe rather than actually developing the techniques ourselves. But there's some activity in that area as well, and that's what we're doing. So thank you very much for your time. If anyone's interested, there are links available, and you can follow us all on Twitter and stuff like that. Any questions?
Just had a quick question. I know you said about safety and at the start. Apologies for being late. Was just around the number one, obviously accuracy of the data, but also the ethics behind it. And in terms of, like you said, you put in Nicola Sturgeon, you get Sturgeon out. Is there's that side of also the privacy of, you know, recognizing that specific person, but also around the defects that we said agent-based modeling is sometimes you don't get that accurate data because the people that's putting it in, you know, they have a certain representation or, you know, human error. How does this kind of minimize that, or does it? And or what kind of pitfalls can we still expect from this?
So, quite a lot of answers to that question.
Yeah.
So there are, in terms of the safety aspect, in terms of not just having what tend to be called in machine learning granny cells that sort of you know learn the particularities of one person. There's quite a lot we can do there. So there are ideas like differential privacy that add noise to data before it goes in, and there are mathematical proofs that you can do that certain algorithms are statistically almost certain not to produce stuff that violates privacy. Now, that's not good enough for us, in that even if the maths proves that the correct implementation of the algorithm wouldn't do it, we're concerned about what the actual implementation of the algorithm does as well. And there's always the danger that the algorithm doesn't fully meet the properties of the mathematical thing. So we're not happy with just trusting mathematical proofs in the same way that you can get cryptographically perfectly secure schemes, but the implementation has to be perfect in order for that actually to be safe. So there are lots of other things you can do. One of the if you run so there are two different modes in which you can use synthetic data generation. One of them is you can do the generation when you still have access to the original data that you trained from, and the other one is you can take the generator outside and run it safely. And there are pros and cons of both of those. One of the advantages of running it with the data is that you can then check that nothing that you generate is very close to anything in the original data. And so that can give you a very strong guarantee that you haven't just reproduced something in the original data. You still have to be worried about have you produced significant bits of it and so forth, but you can check all those kinds of things quite carefully. Obviously, the disadvantage of that is you're doing the generation in the presence of the real data in some sense, even if you kind of separate it. And so you don't have to worry about, well, you know, did you necessarily transfer out only the synthetic stuff, not the stuff that you've validated. The advantage of taking it out is that then you don't have that problem, but now you can only do checks on the statistics of the thing. You can't actually clearly go back and actually check that you haven't generated something identical. There are hashing things that can help with that as well. So people might have heard about the neural hashes, the algorithm that Apple's using for CSAM detection, or proposing to use for CSAM detection, which unlike so the way a conventional hash works is if you change anything in the data, the hash value changes, which is kind of the whole point of the hash. Whereas these neural hashes that Apple's using or proposing to use for the CSAM detection, the whole point of them is that there are various changes that you can make to the image and you still get the same hash back. So there are potentially ways of kind of taking your outputs externally, hashing them, feeding those back into the original system and checking them on the hashes match, which again gives you some stronger kinds of guarantees. So there are ideas like that. In terms of the ethics of it, so there are ethics around machine learning generally, and one of the ideas, so there are lots of different ideas about using these kinds of systems to reduce rather than reinforce historical biases and injustices. Some of those are to do with expanding parts of a data set that are underrepresented or changing outcomes that you think are historical injustices, which are statistically questionable but potentially very good from a social point of view. There are also ideas about just multiplying. So again, synthetic data is a rather broad term. One of the ideas is one issue that we face is with facial recognition systems, for example, being well known to work better on white people, frankly, than other skin complexions. And there are two different possible views on that. One is that really bad for the white people. The other one is that's really bad for the non-white people. But whichever view of that you take, it's probably not great, but it's different for the two. So one of the ideas is that if you can't actually just go out and rebalance the data set properly that you're using for training, because the fact it works better is mostly to do with the fact there are more white faces in the training data than non-white faces in the training data. One of the things you can do is potentially take the non-white faces that you do have and create variants of them, which is not quite the same thing as synthetic data, but it's close to the same thing, and use that to sort of rebalance the data set that can actually end up giving you better performance across the entire base. So there are ideas like that that are around, and that's not very different from some of the stuff that's done again in machine learning, where with handwriting people often rotate. You know, they take one original digit that someone's actually written and distort it in lots of different ways to kind of enlarge the data set that they're feeding in, because it turns out all those rotations and things make the system more robust. So that was a bit of a rambling answer, but it was a slightly rambling question. Rambling, sorry, rambling's unfair. It was a big question. Any other? Yeah.
I just wondering, you call it double synthetic? Sorry, I forgot the name of the.
Oh, so I talk about synthetic doubles. So yeah, in terms of my terminology, I tend to the approaches that start from real data and sort of learn from those to research. I tend to talk about synthetic double, trying to create synthetic doubles of the original data.
So I question on that. Yeah. Have you applied that with any organizations? Have you done any work? Just interested in the case studies you've done and how it works.
So Kafka hasn't yet applied it on any real data. We've been applying it on, funnily enough, on synthetic data sets to start with, because they're the very safest. And secondly, on public data sets. So we're doing things like running it over companies' house data, which is publicly available, and therefore we can start off exploring the safety of the systems in the context of data that even if we do reproduce things that are in the original data, that's kind of not a problem because it's public anyway. We have quite a lot of data that we'd like to apply it to from banks, but we want to finish our testing on public data and on synthetic data before we start applying it to real data, and we need their permission to do that.
Do you have any timeline? Just out of curiosity, in terms of when you think you.
Yeah, so we're actively doing this now. I think over the next, I would expect within 3 months we'll start applying this stuff to some of the real data sets we've had. I don't think we'll be taking anything outside the safe haven initially, because the next thing is we need to build our own confidence, but also the confidence of our data suppliers and indirectly of their customers as well. Because the hope with all this stuff is that it's this incredibly difficult landscape that I think almost everyone recognizes there's lots of power in financial data, and whatever in private data. And there's lots of good that could come from us being much more open and being able to use that statistic to find patterns and redress injustices and all sorts of things. But most of us regard our financial data, this is not sweet. Most of us don't like the idea about tax returns being published and all that kind of stuff. So we have to be very respectful of that. And there are even more dangerous things that we might like to do in principle, and that might have big social benefits, but would terrify most of us on real data. So, what if there are lots of interesting things you could do by linking people's financial data and their health data. Right now, almost none of us would want our actual financial data linked to our actual health data. But if we could find a way to do that safely with synthetic data and understand, because we know that finance impacts on health and health impacts on finance. And if we could end up, saving more lives or improving people's lives better, or helping tackle financial problems that occur for people with mental health problems, all that kind of stuff, through bringing that stuff together in a safe way with synthetic data, maybe that would be really good. And we're super cautious about that, because the last thing we want to do is screw up and harm someone through this. But the potential is just too exciting and not to be as well. And we're not anywhere near linking even synthetic health and financial data. But those are the kinds of things that there is potential to do if we could all convince ourselves it's safe. Yeah, so I think I have to wrap up at this point. Thank you very much all for coming. I hope that was interesting. I'm sorry, it's probably a bit cold.
Very good.
Thank you.
Thank you, Nick. Thanks, Sid. Thank you. Yeah, very good.
Yeah, sorry if there was more on the technical stuff than.
No, I was interested. We're talking about machine learning, apprentice school.